Hi! In this unit, we're going to look at the electronic structure of atoms. We've just finished with nuclear chemistry, so we've spent a lot of time in the nucleus. But now we're in Unit 5, and we are looking at Video 1 and electronic structure in atoms. The purpose of this unit is for us to learn about the arrangement of electrons in atoms. The theory of the arrangement of electrons has been based on the study of light that has been given off and absorbed by atoms. So first of all, we're going to have to do a little short review of light and the properties of light. We're going to look at light in two different ways. We're going to look at light as waves, and then in a little bit we'll look at light as particles. Well, visible light is the light that we're most familiar with. It's part of what we call the electromagnetic spectrum. And all types of electromagnetic radiation in this spectrum can be described as waves. And the visible portion of the electromagnetic spectrum is just a tiny part, as you can see down in this diagram. The electromagnetic spectrum can have wavelengths that are very long, like radio waves, or can have wavelengths that are very short, like gamma rays. And somewhere in between is our visible light, but it's just a small part of the electromagnetic spectrum. Well, how did we know that light behaves like a wave? It's a very old experiment from the 1800s. Thomas Young did a double slit experiment, and he showed that light could interfere with itself and therefore behaved like a wave. Now, you already heard me say the word wavelength. And so what is wavelength? And we need to learn some properties of waves. Wavelength has a symbol lambda, and it's in parentheses here. That's a Greek letter, and you need to be familiar with lambda, so when you see it, you're not wondering what it means. It is the symbol for wavelength. And wavelength is the distance between any two identical points of a wave. So peak to peak or trough to trough. So if you look down here, the wavelength would be from the top of this wave to the top of the next wave, or from two identical points on the wave down here. That's the wavelength. The unit would be meters. Now, when we were talking about the visible light in the electromagnetic spectrum, its wavelength in nanometers would be anywhere from about 400 nanometers to 800 nanometers. Now, another property of waves is frequency, and the symbol for frequency is nu, and it's a Greek letter as well. It kind of looks like a V. Frequency is the number of waves, so how frequently do the waves pass a given point per unit time? And so the unit for that is 1 over a unit of time, which we're going to use seconds. 1 over seconds, or seconds to the -1. It has a special name called hertz. So inverse seconds are hertz. Well, the speed of waves can be given by an equation. And the speed of waves will be a constant, and it's equal to the wavelength times the frequency. So we're going to use this equation some in class. Now, if the wavelength were to go up, the frequency would have to go down for their product to be a constant. That's what we call things that are inversely proportional. When one thing goes up, the other has to go down. What does that look like graphically? Well, down here on this graph, we see that frequency is plotted on the y-axis, and the wavelength, lambda, is down here on the x-axis. And we see that it's not a straight line at all. Now, how can we make this inverse relationship make a straight line? Well, you could plot the frequency versus 1 over the wavelength, or the inverse of the wavelength, and then you would see the straight line. So these are graphs that indicate that frequency and wavelength are inversely proportional. Now, sunlight. Isaac Newton was a person who introduced the idea that sunlight, or white light, or the visible light, can be separated into the different colors of the rainbow. And he used 7 colors: red, orange, yellow, green, blue, indigo, and violet. And he did this using a prism. And so what he saw is all the wavelengths of visible light in the electromagnetic spectrum. And we call this a continuous spectrum. So that sunlight that contains all those wavelengths of visible light is producing a continuous spectrum. And this is important because later on we're going to look at something that's not a continuous spectrum, but it's called a line spectrum. And you can see that below this continuous spectrum where you just see lines of certain colors. That's called a line spectrum. All right, here we've got the electromagnetic spectrum. And so if we look way down here, long wavelengths, that's called radio waves. They're pretty infrequent, so the frequency is low. So long wavelengths, low frequency. Now, microwaves are next. Their wavelength is a little shorter. Then infrared, and then here comes that tiny part of the electromagnetic spectrum called the visible region. And the longer wavelengths would be the red light, and then the shorter wavelengths would be the violet light. And above the violet light is ultraviolet light. So we're getting shorter and shorter wavelengths, and the frequency is going up. Then we have X-rays, and finally, with the shortest wavelength, the highest frequency, are those gamma rays that we talked about in our nuclear chemistry unit. So this is the electromagnetic spectrum. And the speed of all of that electromagnetic radiation is a constant, and it's c, which is called the speed of light, and the value is 3 × 10⁸ meters per second. Well, remember, we said that the wavelength times the frequency of light was going to equal a constant, and here is the constant. The constant is c, 3 × 10⁸ meters per second. And we're going to do some problems with this in class. Now, I said that we're going to discuss light as two different things. So we've discussed light as a wave, and we've looked at wave properties. But now let's look at light as a particle. So light can be described as being composed of particles that are called photons. Well, this idea came about in 1900 by a scientist known as Max Planck. What he said was that every photon of light had a quantum of energy, or just a specific amount of energy. And he came up with an equation, and that energy, or that E, of each photon of light was equal to a constant, h, that's known as Planck's constant, times its frequency. And the value for Planck's constant is given here below. It's 6.626 times 10 to the negative 38 joules times seconds. So what we see here is the higher the frequency of electromagnetic radiation, then the higher the energy. So if you remember, those gamma rays had a very short wavelength, which meant that it had a high frequency. It would have the highest energy. Again, we're going to use this equation in class as well. All right, let's look at evidence for light as a particle. Well, there was something called the photoelectric effect, and what that was is that when light would strike a metal, if it had enough energy, electrons would just be knocked off the surface. Electrons were only knocked off if the light had enough energy. So we were looking at, light that had the shorter wavelengths or the higher frequency. Here's just a little diagram of light coming into the surface of a metal, and those little gray spheres are electrons in the metal, and if that light had enough energy, if that light's frequency was great enough, or the wavelength was short enough, you can think of it either way, those electrons would come off the surface of the metal. And what's just as important is that electrons were not ejected if the light didn't have enough energy. No matter how long they would shine the light or the intensity of the light, those electrons would never come off the surface. So wave theory of light could not explain this. So along came Albert Einstein in 1905, and he used Planck's idea that light behaves like particles. So they're photons with specific amounts of energy. And that photon, when it strikes the surface of the metal, can transfer its energy to an electron when it collides with the metal and pop those electrons off. And this is known as the photoelectric effect. If the energy is great enough, that electron can be liberated from the surface of the metal. Einstein won the Nobel Prize in Physics in 1921 for this work. So, is light a particle or is light a wave? The answer is yes. It's both. Light has particle characteristics and wave characteristics. And this is known as the wave-particle duality of light, which can be kind of mind-blowing at times. Well, this is our introduction to electronic structure in atoms, but we had to first understand light and wave properties in order for us to understand electronic structure in atoms. We're going to practice some of those equations in class. Bye.